It's okay.
28 minutes. Oh, we lost half.
Never mind, it's okay. We'll just learn from this. Okay, the next section we need to go on is this part. Just keep an eye on it. The next section that we're going to go on is the part on interference, which is very important.
That sounds so hardcore.
Yeah, it's really, really important, trust me. Okay. Before we can understand interference and whatever there's to come, can you please impress me by remembering what is the principle of superposition? Anyone? Principle, add together. Come on. It's more than that. The principle of superposition states that, come on, give me fragments of words.
Vector sum.
It's vector sum, same wave, same kind of wave. What else? Displacement. So same kind of wave, displacement, vector sum. What else? What else? Principle of superposition. State principle of superposition. Okay. Important words, you got it, but you need to string it up. The principle of superposition states that when two or more waves of the same kind meet at a point, the resultant displacement is the vector sum of the displacement due to each wave independently. Okay? We'll use that later on. Now, but before that, I would like to go through this phenomenon called diffraction. This is such an important phenomenon which I'm going to show you later on. Why? Very simple idea. Basically, if you have a wave that passes through here and you have a hole size which is A that is very much bigger than the wavelength, the wave will just pass through without any bending. Now the interesting thing is what happens when you close up the gap such that it is comparable to the wavelength. A is still bigger, but it is not so much bigger. So what happens is that it starts to spread. And then when you have a hole size that's exactly equal to the hole size, then you actually get circular wave, where A is approximately equal to lambda. This is called diffraction, which is the bending of wave as it passes through the hole. Single slit diffraction. But we'll go into greater detail in now topic 9.3, I think. Yeah. There's a reason why this is so. The critical point is when A is equals to lambda. That's when it becomes fully spherical. A is the size of the hole. The size of the opening. Lambda is the wavelength. We have wavelength, yes, correct. Okay? So what we have over here is that you need to know that it is the condition, the one that determines is the ratio of A to wavelength. Now that's the reason why if you look through the door, you can't see round the corners. Why? Because light, the wavelength of light is very much shorter than the size of the door. So light doesn't bend around as it passes through the door. However, sound wave, what's the typical speed of sound in our environment? 330 meters per second. And what's the typical voice frequency? 10 decibel. No, frequency, come on, hertz.
Actually, for you, maybe 60 or 50?
No, not that deep. 60 or 50 will be like, hello, are you? If I speak like this, it's about 1,000 plus. 1,000 to 1,000. About 1,000, plus minus. In fact, our ears are designed to resonate with frequency best about 1,000 to 3,000. The length of our ear, the inner ear, the outer ear, the inner ear, sorry. So, our speech frequency is about 1,000 hertz divided by, 330 divided by 1,000. So you have about 0.033 meters wavelength. Now that is about 3.3 centimeters. So that's why if it passes through gaps, it can bend around. It can bend around. Yeah, so that's why we can hear round corners, but we can never see round corners.
So lower sounds will be.
Exactly. So that's why whenever you go outside a movie theater, whenever the gong gong, some movie theater, movie hall has those kind of heavy blast, you can actually feel it, but you don't know where it's from because it spreads everywhere. You cannot triangulate where it comes from. Huh?
That's why all the sounds came the hall, but all the high voices you can hear.
The high voices you can't hear it. Yeah, that well. Of course, if it is very loud.
Voices you'll be able to hear better.
Well, it's a combination, I think. It's a combination of how loud and where you're positioned. But generally, low frequency sound travels much faster, much further. and it bends around much better.
Oh, it bends around.
It bends around much better.
Oh.
Correct. Yep. So, but actually, if you think about it, how would the world look like if light can bend round corners? If you can see round the door, how would the world be different? No, I'm not talking about seeing round 90 degrees. I'm just saying bend a bit. Right? Say for example, if I look through the door, I can see the people at the lockers. No, hang on. This is TOK, huh? But your world will be designed in such a way where it is for the world where light bends around corners. The design, the door design, the locker design, everything will be designed in such a way where it will block away unnecessary people from looking into whatever they're not supposed to look into. Yeah? So, okay, my question is, if you're living in a world where the light bends slightly, how do you know whether the light bends slightly? Because everything has been redesigned in such a way where it will block off things that you're not supposed to see.
I mean, the people who redesigned it will know.
Sorry?
The people who redesigned it will know.
Ah. Okay, that's if you go from this world into that world.
But then
if you're born in that world,
it's like if you're born into another world with the color swap, you won't know.
you won't know exactly. So how do we know? Yeah, exactly. How do you know? Okay, before we go too deep into that discussion, is it still recording? Okay, good. Excellent. Thank you. Okay, now, why on earth do we have to know this? Why is it so important? Now, if you take a look at this two thing over here, source. Yeah. Now, what happens if it doesn't spread? It will just go right through, right? It wouldn't overlap. But we want it to overlap. Yeah, we want it to overlap so that they can superpose onto each other and then produce some pattern. Then we can study. So, which is not interesting at all. So we want it to pew.
This is so notorious.
Yeah.
Destructive.
Destructive and constructive, yes, correct. So why is it important for us to have destructive and constructive? Because we can study the nature of light. Now, the beautiful thing about physics is that it actually, sometimes it comes out with a set of equations that let you measure something that you can't see using something that you can see. Yeah, I'm going to show you in a short while, actually not a very short while, how we can develop equations out of this to allow us to measure the wavelength of light. You must remember that the wavelength of light is about 400 nanometers to 700 nanometers. How small is 700 nanometers to 400 nanometers? If you take 1 mm, cut it into 1,000 pieces, that's still only 1 times 10 to the power minus 6, which is about 10 times bigger than the wavelength of light. You have to cut that into another 10 pieces before you approach the wavelength of light. You know how small that is or not? And these people over here, they have actually come up with a law that allows them to measure the wavelength of light even when the best instrument they have is probably micrometer. So that's the power of physics. If you have good physics, it allows you to measure things that you can never even measure with current technology. Yeah, so that's solid physics. So what is the rule governing all this interference? This is exactly what we're going to talk about. What do you see over here? This is what we're going to talk about. Ken? Ready? Okay, let's go. Whoa. Important. Now let's imagine this point X over here. Let's consider two sources that are in phase. All right? I'm going to go through the simplest case and then we're going to go to the higher order cases. So the sources are in phase over here. So the wave comes out like this, wave comes out from this source over here like this. Let's consider this as Y, this as Y, this as X. Now consider the case where Y minus X is equals to one wavelength. What will happen? The wave from S1 and S2, the wave from S1 or S2 will reach first? S1, yes, correct. So S1 will reach the screen first and S2 will lag behind by one wavelength, right? Okay, so it will lag behind by one wavelength. Now can you see that when this portion reaches the screen, this will reach the screen as well? So they will interfere? Excellent. So they will reach the screen and give you this. You okay? So this is what we call constructive interference. Now there is a higher order condition over here. Can you see that this will be the case even for 2 lambda, 3 lambda, 4 lambda, 5 lambda? Yeah. You'll lag behind with just one more. So the condition for constructive interference is that it must, yes, correct, satisfy this. Very important condition. I'm sure that this is inside your notes. please highlight that. Yeah, correct. Highlight that portion. That's the kind of thing that you must look out for when you revise. And those are markers where you can tell yourself, if I know this, I know part of 4.4. Yeah? Highlight that portion. Now, let's consider another point. This is B, this is A. Let's call this point here. Now let's consider the case where B minus A is equals to half a wavelength. For some reasons, I mean, it is not drawn to scale, bad scaling, but let's consider it. Okay, half lambda. So when the wave from S2 reaches the screen first, can you see that the wave from S1 will be lagging behind by one wave, half a wave? Slightly off. You see? Nicely, yeah. So it will give you nothing, yes, correct. So this is what we call destructive interference. Now, the same thing happens 1.5 lambda, 2.5 lambda, 3.5 lambda. Exactly. So path difference equals to n plus half lambda. It will give you destructive interference. Now you must know that there is a very important assumption over here. Think about what will happen. Okay, we'll come to that later on. Think about what will happen if the sources are not in phase. Instead, they're out of phase.
Then it'll be opposite.
Yes, correct. The condition will be swapped around. Now, how in exams am I going to test you on that? That's important, right? You must know how we can test you whether you know this swap. So, this is what we're going to tell you. It is exactly what I'm going to tell you if I set a question on in exams. I will tell you that point O, no sound. What can you deduce from point O is right in between the two sources. What can you deduce about the sources? They are out of phase, yes, correct. So the litmus test whether the sources is in phase or out of phase, look at the point right in the middle between the two sources. If this O is loud, it is in phase. If this point O is soft, it is out of phase. Why? Exactly. I was just about to go through why. Yeah.